John, how can you always have the right TV for the right application without carrying hundreds of valves on your truck?
You can carry the hundreds of valves on a trailer behind your truck.
That's too funny. That would work, but how are you going to do that? Maybe there's an easier way.
You can use Sporland's interchangeable cartridge style Type Q and Type BQ TEVs. Type Q is a conventional design and Type BQ is a balanced port TEV.
Well, come on, I need easy. How easy is it?
Easy as 1, 2, 3.
And it serves thousands of unique applications. So what's the process? How do I put this together?
First, you select the thermostatic element assembly. Then you select the body that you need. Then you select the right size cartridge for the application to get the proper capacity TEV for your application. And then I guess it should also be said you want to actually assemble those into a single valve.
That'd probably be a good idea.
Indeed.
These easy to select and assemble valves mean you're always carrying the right valve for the right job then. If folks want to learn more, what do they do?
You can go to sporland.com and find more information on the Type Q and BQ thermostatic expansion valves.
I guess that's Jim and John for Sporland signing off.
We've all been there, in the middle of a job, everything going smoothly, until boom, you're missing a part. United Refrigeration is your one-stop shop for all your refrigeration needs. Use your computer or smartphone to go to www.uri.com at any time of the day or night to check stock on your favorite brands, such as Copeland, Sporland, Carlisle Compressors, Danfoss, Emerson CPC boards and sensors, Carrel, Hussmann Parts, and K2 United Refrigeration Inc. is home to these brands and many more. Looking for information on refrigerant conversions or refrigerant banking? Quick access links on the homepage can get you to the information you need. All approved accounts are able to see live to-the-minute inventory and pricing. Product not in stock at your local branch? No problem. Use the Nearby Stock feature to find a local branch that does have what you need. Are you looking for a branch address, phone number, or after-hours number? That's all available as well. Just click on the branch locator and search for your local branch. Have a model number and looking for a replacement part? www.uri.com/ARP has a vast list of quick pick replacement parts. Just search for the model number of the equipment you're working on and click the Replacement Parts tab. If you don't have an account, click the Register button and we'll have you online in no time. With more than 400 locations in North America, each United Refrigeration branch is fully stocked for immediate pickup. Our branch employees have in-depth technical knowledge, so we can help you get what you need when you need it. Visit your local store or www.uri.com/ARP today. United Refrigeration Inc. has all your solutions down cold.
Yeah, I mean, that also won't help you in the windy cold conditions. At least the adiabatic is some buffer to the wind. So an open coil is, yeah, it's gonna pull the wind towards it.
What's that?
Want to parlay into high ambient strategies?
Yeah, let's talk about high ambient strategies. I know a bunch of people have already talked about it, but I mean, I want Bob's perspective on that.
Yeah.
So I
no, cool. So
go for it. Sorry. Because we briefly talked about this, and I had asked you about some methods that are out there right now, and you know, we have parallel compression, we have that SkyCool system, you have heat reclaim is acting as one of your high ambient strategies, that big Danfoss ejector type system, the regular, you know, old school ejector systems. I want to hear it all. I mean, you know, you did some white papers for some consulting stuff where you basically ran the benefits of what system would be more beneficial where, correct?
Yeah. So we did look at that with Emerson and on typically like a high ambient strategy on what makes sense, especially in North America, because like you said, now you got anything from Texas and Florida all the way up to, well, typically Alaska, also worst case scenario. So there is a big spread of multiple ambient conditions across across North America. And the funny thing is, if you ask anybody if they got a high ambient, I've never heard anybody not saying that they're not in a high ambient climate. Even if you ask someone in Chicago again, they will tell you like, yeah, man, last year summer like 105, we were dying in the heat. So everybody will tell you like everybody claims they got a high ambient condition. So firstly, the outlook or my standpoint with high ambient strategies is like, I think they're all good. And I mean, we can go into them now, but I think they need to be understood how they work, number one. And number two, you need to look at it on an annualized basis. And again, it also comes on how you design it into the system. So the main thing is to look at it on an annualized basis. I mean, the total refrigeration systems run 24/7. It doesn't run just during the day or during the night or only in summer or only in winter. Obviously, it runs harder in summer, it runs less in winter, but at the end of the day, it never shuts down. So you need to look at it for the 8,670 hours that it's operating. And I mean, if you go and look at that, what average, how can I say it? If you go and look at most globally, you look at the average ambient conditions that there are, you actually would be amazed on what the annual average temperature is. It's way at the bottom of a subcritical operation. I mean, let me just open my.
Wait a minute, you just rattled off how many hours are in a year?
Yeah, I think it's about 8,670 hours, thereabout. If I'm correct, I hope I didn't screw that up. So that's
fact checking right now.
Cool.
Sounded
I'm gonna get my conversion out. I need to convert now Fahrenheit and Celsius, otherwise I'm gonna get
8,760. And I know Wayne used a bar before, and if anyone doesn't know that there's, for every 1 bar it's 14.5 psi. So before he was talking about a half a bar. So just to make sure no one caught that, if you're going to ask me for the Fahrenheit to Celsius conversion, that is done on my phone. So I'm sorry, I can't.
Yeah, no, I'm still getting used to that as well. So that's why I thought because I mean, even if you take South Africa, take Johannesburg, I mean, Joburg is considered a high ambient condition. I mean, we don't go below freezing in the winter. It's nice and warm here always. The average temperature of Johannesburg is 60 Fahrenheit. So that's the average annual temperature of Johannesburg. So that is lower for most of especially in Europe. It's lower, much lower than that. And then also in North America, depending on where you are, you've got that. So I mean, the reason why I'm saying that is if you need to look at the annualized side of like, and when do you really need this? When do you need this? And what combination of them, or which ones do you need, if I can put it that way? Because our outlook is, and that's something I mean, if you go and look at it, it's interesting. I actually would like to do that one day. I'd like to go and take like a picture from system 1 that we did, system 2, 3, 4, like kind of like a timeline thing. So it's one thing that we did learn going on. Like when you started, we threw everything at it. We had safeties and backups and everything that you can have for us on a CO2 system. And as you carried on, you started realizing like, geez, man, these backups just cause headaches, and they're the ones that fail. And you start. So we are quite big fans of simplicity. So at the end of the day, we really look at, if you don't need it, don't have it. Because if you have it and you don't need it, it's just going to come back and mess up, and that's going to be the thing that fails. Mm-hmm. And also it's another thing. I mean, if you look at the massive task that everybody is taking on, I mean, you speak to some guys, there's ridiculous goals. Like I'm all for it. I love it. I mean, but everybody overnight in the last 2 years went from, yeah, we'll see where it goes, and CO2, we believe it is the way to go, and we have our strategies, now to, dudes, we've got 20 years and everything needs to be changed. And there's like, what, 40,000 retail stores in North America alone that everybody wants to change in the next 20 years. I'm like, how is that going to be happen? Like, the only way that you can do that is there needs to be people in the field that can do it, and it needs to be able to be supported. And that's why I believe in simplicity. Like if you have simple systems that firstly don't cost as much as they would with the other systems, but secondly they're easier to understand, they're easier to roll out, they're easier to get techies to work on them, and they're just easier to understand overall. So we are, sorry for a long introduction, like we really are would love to take a simplicity outlook on it. So if you want to go then delve into high ambient strategies, like I said, basically all of them is based around mitigating the flash gas of a system in when it is how can I say it, in transcritical operation mode. So again, to get away the false or the facts that's out there saying that CO2 can't operate at high ambient conditions. It can. The thing is just you do lose your efficiency, but you can pull it back. But it's nothing that says it can't operate when it gets that warm. I've heard that a lot where people say like we need to have these systems and these high ambient strategies in place, otherwise the system won't work when it gets to those temperatures. It will. You're just not going to have the most efficient system. So I mean, number one, if you look at what is the simplest high ambient strategy is adiabatic gas coolers. I mean, when you look at it on the high side of life, there's a big reduction of it, and there's a big reduction on where you operate. So what we've found and what we saw on most of the studies, and I mean this includes Chicago, all your drier areas. So basically, the only place where an adiabatic system don't work as well as it should work is where you've got the humidity. That's just because your wet bulb and dry bulb differential is not as big. So your adiabatic system don't do as much as it can. So that is your Florida areas, that's your Texas areas. Outside of that, you've got fairly dry ambient. I mean, even California area side of life. So basically what we've seen and what you can look at if you go and look at his bin data is most of the, like 80% of, I would say, in North America, you will operate less than 2% in a transcritical mode once you have adiabatic on, once you do utilize water as adiabatic gas coolers. So for me, that is mitigating high ambient strategy. You're pulling yourself completely out of transcritical operation.
Weren't you also telling us about some method where some manufacturer or some customer was utilizing, you know, for the adiabatic cooling, they were actually utilizing some of the water that they were getting out of the evaporators, the drainage. They were actually storing that water instead. So not only are you not wasting brand new city water, but that water is going to be at a relatively cooler temperature anyway. So you're getting a little bit more efficiency out of that. Is there a lot of people doing that in Europe, or where have you seen that being utilized?
Strangely enough, it does not get done that much. We do it a lot. Always recommend to do it because that is the big negative factor of an adiabatic gas cooler is it utilizes water. So I mean, water is a part of your sustainability goals. It's a commodity. I mean, you can't waste water. So I mean, it's actually a group of Walmart companies. It's company called Macro in South Africa, which we do a lot of work for. So they're a large wholesaler with quite a significant freezer and medium temperature food section. So basically what we do is we recapture the condensate that comes back out of the off of the evaporators, which is a lot. I mean, you're constantly generating water. We take that water back, simple filtration system. We store it in large tanks, and because with adiabatic you can control when you utilize the water. We haven't had a case where we didn't bring enough water back to supply the gas coolers throughout the year, if you have a bit of storage around it, obviously. So I mean, in this case, basically the store ends up utilizing no municipal water or no potable water that goes into the facility, we actually utilize some of the excess water. They utilize it to irrigate the gardens and do some other things that they want to do with that water. So they actually water positive at the end of the day. I mean, in South Africa we don't, but in the US I know you guys also have the whole sewage and stuff that comes into a operational cost factor. So I mean, if you also can utilize the sewage system less, there is actually a cost saving to the client there as well, where you don't put all this water and stuff down the drain. You actually utilize it back in the facility, and you don't use potable water back into the facility. I mean, that can be, if you plan your facility correct, that can be the additional water that you don't even use on your adiabatic gas cooler can go to urinals or toilets and stuff like that. So yeah, I mean, that water is there. On top of it, if you still want to, you can also capture rainwater if you want to store that. Don't know, I've heard it's somewhere illegal, but I don't know if it's still illegal everywhere. But bringing back condensate water, definitely, we found 90% of the time, even in industrial applications, it serves more than what we require on the adiabatic gas coolers. And we do not have to utilize potable water for that. So yeah, that's one way to mitigate around using the water. So that's a nice side of it, because the adiabatic doesn't use a lot of water. If you control it properly, you don't need to use it all year round. You use it when you need it.
Usually above what? So it's 74 degrees is usually what the controllers say, right? Usually when they start bringing on the actual water.
Yeah, no lower than that it's required. So only above that, so I mean, again, on average, if you're going to look at most of the places, like you're going to run and utilize water 30-40% of the year, not even that much. That's talking like your California areas and stuff like that, where water is a problem. You're looking at 30-40% of the year only to utilize water. So it's not a lot. If you keep on, if you allow for enough storage, and you allow for bringing that condensate back, then yeah, you got that water when you need it.
So you said about, different areas require, or work better with different types of high ambient strategies, right? So answer a question for me. Why up in Canada do they have tons of ejector systems down here? And I think I've never seen one in like down in the States, other than the Danfoss trainer that they have. Why is that?
You're talking high pressure ejector or low pressure ejector? Like
high pressure. It would be in between the gas cooler and the HPV.
Okay. Yeah. So I mean, honestly, I don't understand. I wouldn't see a use for it in Canada. Although your summers still get high, but again, I think a lot of it is mitigation of, and I think to Kevin's point, mentioned it's a mitigation of the water not wanting to use water,
Okay.
which I understand. But the thing for me is if you can bring that, so because they literally will have that ejector in place for 5% of the year. It will only work 5% of the year. Because again, like I said, yeah, go for it, Kevin.
Do they actually get the benefits and the cost savings that they say they get out of running an ejector? Because I've heard it's 50-50. I've heard guys say that they don't get the benefit of running it, like they don't get it back, or it's just not as efficient as everybody says it is.
That again comes down to design. It comes down to how you design your system. Again, if you're going to design your system, like we said, at that upper level, you're taking away the working of your high ambient strategies. It's the same with parallel compression. I've seen a lot of systems that goes out with parallel compression, and if you go and look at the runtime on the controller, it's run 5 hours in its life. Maybe it was with commissioning.
Damn.
It's just been sized wrong. It's a cost mitigation. There's one compressor on the parallel side. What happens in a retail store? You design for 100% capacity. Store ends up utilizing 50% requiring 50% of the capacity that it's designed for. You have one parallel compressor because you didn't want to make the system costly, or I don't know. And now that compressor is just completely oversized and it will never run. The only time a parallel, because that's the thing, a parallel compressor will only run if it's on a VFD and at the 30 hertz or the 30% of the capacity of the compressor matches the flash gas plus buffer. So that compressor won't come on if there's not enough flash gas. So like I say, I mean, if you have, and then you have parallel compressor, and it's added in a condition that's not that high. It's added in a condition where it's quite dry, and they've added adiabatic gas coolers onto the facility. So that parallel compressor is just a spare compressor in my mind. They're not like most of those compressors just end up replacing a compressor on the medium temp and never being replaced again on the parallel side of life. That I've seen a lot. Unfortunately, I've seen that a lot happen. I've seen a lot of times where parallel compression runs beautifully and works really well. I mean, where it's been designed properly, the application, the place, the location, everything was just perfect for it. And then obviously you've got the strategy where you can put your HVAC onto that, or you can put chilled water onto that. Then yeah, I've seen parallel compressor work really well and take care of that flash gas and additional cooling loads very well. Then again, your ejector and then adiabatic gas cooler works on reducing your gas cooler outlet temperature. Excuse me. And then ejector works on having this high pressure differential. So ejector works optimally when you have a high gas cooler outlet temperature. Adiabatic gas cooler and a parallel compressor system as well. Parallel works optimally when you're running at the high ambient condition. The more flash gas, the more it can take care of it, the more savings, the more percentage of savings there are. So you basically, well, I guess what I'm trying to say is if you have adiabatic gas coolers and you make that work, you really need to think about if there is a need for any additional high ambient strategies. One thing that I think you see too little is everybody forget the low side strategies. So that's why I asked you about the ejectors. Like ejectors work very well on your superheat side of life, on creating a higher saturated suction temperature, and that's a 365 that's non-dependent on ambient conditions. So there's a lot of strategies that's on the lower side around the liquid side, the evaporator, the receiver, that in my mind, sometimes if you look at it, it's a 3%, 4% benefit compared to the standard side of life. But annualized, it's a all year round benefit. I think technology shouldn't be sold for what they can do in an instant manner. They should be sold what they can do for you on an annual basis. So, I mean, even like I said, adiabatic gas coolers. At the end of the day, if you're going to look at it, they can bring you a 20% energy saving. If you go and look at a really high transcritical operation, you're going to go and say like, okay, cool, we're sitting at an 86 plus ambient condition. We can get 20% energy saving, but stretch that out over a year, maybe that technology brings you a 2-3% saving. Is that worthwhile? Does it make the system too complicated? So those are all the questions that you need to kind of answer. And to throw all these technologies onto one system, I think you're just complicating life, and I think you're just making it too hard for people to understand.
Well, I just want to bring this up for an example. So in case anyone's like, what the hell is a high pressure ejector system? What the hell is a low pressure ejector system? They can actually see it. So if you do go to YouTube and see this video, you will see an example. So here we have a high pressure ejector system that you were talking about. And then here is another example of now the low pressure ejector system.
Today's episode is sponsored by the Refrigeration RDP Series differential pressure monitors from Westermeyer Industries, now available for transcritical CO2 systems in addition to other common pressures and refrigerants. When the filter element of your coalescing oil separator is contaminated, it can hurt your system's performance and efficiency. But how do you know when it's time to replace that filter? Wait too long to replace, and you could end up with a nasty filter blowout. But replacing too often can be a waste of time and money. The answer is installing a differential pressure monitor. The RDP series differential pressure monitors, including the new transcritical CO2 model, are available now from Westermeyer Industries. To find out more information, email sales@westermeyerin.com. That's WESTERMEYERIN.com.
And I didn't understand how this worked until I actually had a talk with Ignacio from Kaiser, because this is basically similar to almost like an FTE tank, right? I mean, it's the same principle, right? Because then they can raise the pressure. I think on the low pressure systems, they also float the flash tank bypass, or can't talk, flash tank pressure. They float that up, correct? When they're utilizing the low ejector system.
Yeah, you will match it in the lift that you can get. Yeah.
Okay. So, like I said, I just wanted to show that for an example. Basically the difference where you can see they have this extra accumulator here in the low side ejector system versus the high pressure. That's all I wanted to show. Sorry.
But it's no. That's good to know. But again, like I need to say, you need to. It's all these technologies are interesting, but you need to try and understand how they work. In terms what I'm trying to say is like let's put it this way, the simplest system for CO2 that is available in the market is your standard DX transcritical booster system. No parallel compression, no anything else. Some internal heat exchangers for subcooling, like we discussed in the beginning.
Mm-hmm.
Like that is your simple system. Everybody understands DX. So the only thing that you need to learn, Brett, you would know from like training and stuff like that, you need to let people then understand the difference on the high pressure valve and the flash gas valve and how you control that receiver. That's the only difference. And transcritical operation, no pressure temperature correlation. That's the teaching from HFC to CO2, and don't stress about the pressures. It's okay. Like once you pass that and you get your hands on, things go faster. All these other technologies do, again, like I said, they bring a very high level of complexity in some cases. And you need to understand, like you said, like the FTE, the low superheat ejector systems, all of that, they work, but you need to understand where they work from and how can you design your system. It's always an interesting factor. It's one thing. Those type of technologies was introduced because Europe predominantly had their cabinets specified at a very low operating temperature. So if you had a DX system in Europe, they would specify that you need to run for, sorry, I'm just making conversions here. So if you want a product temperature of, let's say, about 34 F, which is just above freezing, your standard meat or veg and that kind of stuff, their cabinets would specify that you run at -8, which is, call it 18 F.
Okay.
Which is bad. I mean, that's shitty. That's very low saturated suction temperature for a fairly high product temperature. But that's what the cabinet specified for a DX specified system. So once you can make a system semi-flooded, which is what the FTE and the low side ejector system do for you, you can increase your saturated suction temperature. The interesting thing about the US is you guys got very good evaporators and you got very good cabinets, and your specification is already for 25 for the same product temperature.
Well, so we've had a problem with some of the manufacturers doing the engineering, and they'll engineer it. They'll engineer one case that's designed to run at, let's just say, a 26 degree Fahrenheit coil to get a 30 degree discharge air, because it basically has only a 4 degree TD. But then you still have to operate at that plus 16 or plus 18 for your lowest SST case is just typically your meat holding box, right? You know, typically those are hanging evaporators. They have a 10-degree TD. So you have to maintain 18 to maintain 28, right? 28-degree box. I haven't seen very many EPRs in CO2, and because of that, you know, basically they'll size the coils for it running the 26-degree saturated versus the 18, and then find out that the orifice is not the correct size. So, I mean, do you, in industrial and what you do on the regular, do you use or spec any EPRs in there to you know, kind of mitigate some of that sizing issue?
We optimize the evaporators. So
Very good answer.
so that we don't have to run at that shitty low saturated temperatures, because that is a big saving. I mean, for every 1.8 F lift in saturated suction temperature, you can have about a 3% energy saving annualized.
Well, you lose mass flow too, because if you're operating so low at a saturated suction, you know, the expansion valves that are being controlled by these case controllers, what do? They mitigate superheat until they get down to their superheat, and then when the case temperature gets down too low, it shuts down to either a min percentage or absolutely freaking nothing, so it doesn't pull that case anywhere lower down in temperature. So, you know, you're basically going from all your medium temp could be you could probably have maybe about 5% running out of your whole medium temp load, because you're basically, your lowest case load is the plus 18, and then you got all these other evaporators that are supposed to be running at a higher saturated suction, but in turn do not. So your answer is, we don't design it shitty, we optimize it.
I mean, that's my biggest complaint, like with CO2, is with the case control side is ends up controlling temperature with the metering device, and then it just, the mass flow goes in the tank, and then the load goes in the tank. I mean, I would love to see some more EPRs, and we have a couple stores where we have them. They run amazing.
Yeah, no, look, use them myself as well, and they do work, and it is something that needs to be implemented, because the low side gets overlooked. I think there's, and I mean, don't get me wrong, like, again, I'm not against any high ambient strategies. They work. We use them where it's needed, how it's needed, and when it's and if we need them. I'm just trying to say, like, there's more to a system than just the high ambient strategies, and everybody overlooks the low hanging fruit and the benefits that's right on the table. So, I mean, again, like, so if we look at a standard retail store, our go-to is about 23 F saturated suction temperature for the medium temp.
Okay.
That's our design point, and we will float it up. So if we can get it better, optimize it, if load is better, all of that kind of stuff. And that's for almost all product that we see around the table. So we look at the evaporator to suit the product instead of the saturated suction temperature to suit an evaporator.
Mm-hmm.
The only place where we do not do that is where you have is on your freezer side of life, where you maybe have your ice cream, something else that needs to run. It's usually, I don't know, 10% of the store that needs to run at a lower and then we would look at a satellite compressor. So we would look at incorporating a satellite compressor that can swing over or add on to the main system, on the main LT system. If that, let's say, that compressor fails or whatever, it can, you have a swing, or you have a backup or a solenoid, whatever, it just marries the main LT suction, and it can maintain its temperature until it's fixed. But because, I mean, we're driving energy efficiency at the end of the day. So for 10% to run 6F lower, you know, that's massive energy loss. If you really think of that, yeah.
So I have two questions now. I'm sorry. I keep thinking of more shit as you're talking. So one of the things is, we were having a discussion on if you would have to put some sort of check valve in parallel with an EPR, and electronic EPR. And I wouldn't think that you could, because if you did do that, if it would close down, if the suction pressure on the back end would get higher than what the saturated suction is at the rack, I mean, that's the whole purpose of it. It would start bypassing around the check valve.
You need to check the liquid.
You're only checking the liquid. Okay. So that's one thing. The second thing is you said you optimize the evaporators. When you say that, I'm assuming that you're putting some sort of either mechanical or electronic EPR on there to maintain. I haven't looked at the 5,000 page Danfoss industrial guide in a very long time. Do they make that setup where they have that? It's basically a valve train where you put the different heads on it and make it do whatever you want. You can make it be a hand expansion valve. You can have it do an EPR. You can do an inlet pressure regulator, outlet pressure regulator. You can make it do a whole bunch of fucking magic stuff, including like electronic shutdown. That being said, what are you using?
In retail or in industrial?
Both. I want to know both.
So retail, EEVs, straightforward. Expansion drive, keep it simple.
No,
so when I say we optimize, when I say we optimize the evaporator, I mean we optimize the design. So we basically design the evaporator. We design the circuitry, because you can design an evaporator to supply a certain relative humidity and a certain temperature required at the saturated suction temperature that you give it. I think that, and it's it's not possible. I understand it's not possible overall. We were possible to do it. When we started doing CO2 in South Africa, there was nothing CO2 related here. So everything we needed or wanted to, we had to do it. So we had to end up going to coil manufacturers, and we had to end up designing the evaporators for that. And we just said, like, that's our saturated suction temperature. If we need a coil for this cabinet or this cooler or this is how we're going to design it to give us the temperature, the humidity, and everything that we require at the saturated suction temperature. So I guess I'm putting a task out there to the cabinet suppliers and the evaporator suppliers to go and say, like, you can optimize your evaporators that you can run, I don't know, 90% of the store that's on medium temp and 90% of the store that's on LT at a set saturated suction temperature.
So start taking out fins, so you have less thermal conductivity.
CO2 is perfect. Like, I mean, if you take the standard footprint at an HFC, so the difference is what you need to, like, an upright cabinet. Since 10 years ago, that was a HFC based cabinet. The footprint of the cabinet didn't change. The length of the cabinet didn't change. But now you're putting CO2 in there. CO2 needs half of the space than an HFC based coil. So there's plenty of space for you to optimize. Number one. Number two, they're putting doors on it, on these systems now. The capacity is reduced. So there is so much more space and volume at the bottom to really optimize that coil. And that comes to diameter of your piping. It comes to your circuitry, how you optimize your superheat. You can run a DX system if you design your rack accordingly and your evaporators accordingly. You can almost run a DX system like it is as if it's a flooded type system, because you can really run 3F superheat at the evaporator, because you gain your superheat internally in your system. You get benefits of your liquid subcooling, like we said earlier. So you can it's as good as a flooded type system, if that makes sense.
No, 100%. So when you say less space, are you talking less coil space or less cabinet space?
Less coil space.
Less coil space.
Okay, so we can keep the cabinet the same size because it's still going to be the same amount of BT load. Just make that coil less passes, maybe less fin spacing.
So the CO2 coil is half the size of a DX coil. So I mean, yeah, you could essentially make that coil bigger if you wanted and make it more efficient.
Well, I think a lot of the things that make those coils efficient is the more fins per inch for the most part, like giving you a lower TD, right? Because I mean, if you have more surface area, right? You're transferring more energy from the product, out to the coil, which is then giving you the lower TD. Would that be an apt description?
Yeah, but if you make the coil bigger, not saying less fins per inch, but a bigger coil.
Okay, I get what
You
you're
have
saying.
more rooms. You have more surface area. More.
Yeah, I mean, and like I said, like just the diameter of the pipe and the way you circuit it, because I mean, already you get a smaller diameter, there's already more surface area. So it's not just necessarily in bulk. We're not just talking make it bulk. It's literally just optimizing that surface area. Because at the end of the day, there's no reason why for a certain type of produce, if you can operate at 23F saturated suction temperature, to get yourself a 34F air or for product temperature, you can do that whether there's dairy, meat, fruit, anything. It doesn't matter what's in that cabinet or what type of cabinet that is. Like it's possible to get that. Physics says you can get that, so it is possible to get it. It's just make sure that you get it, or to look into getting it. Yeah. I mean, we looked at EPR if you got like a complete shootout of a temperature, like I don't know, a high temperature requirement, and we didn't put it on parallel compression because we don't have it. Then we looked at EPR, but not these different levels of, here's a row of cabinets that's requires 2F lower or 2F higher or 4F lower or 4F higher, because yeah, that's hard to mitigate that with a system.
So I know you said you're optimizing the coils, but you did say that you do utilize EPRs. Now, what EPRs are you using? Like I said, I know Danfoss makes some CO2 stuff, and I think Hansen started to, did they not?
Yeah, we predominantly use the Danfoss stuff, to be honest,
Okay.
especially in the industrial side of life. There we definitely utilize most of the Danfoss stuff. They got a good industrial range, and like you said, you can build it up, you can put it up, podcast, defrost, all that kind of stuff. You can put through Danfoss and larger capacity. So yeah, we do utilize Danfoss most.
Kevin, my brain hurts. You got anything else? Because I'm broken at this point. These are one of those conversations where I feel stupid. I'm listening to what he's saying. I think I'm understanding what he's saying, but I don't know if I totally get it.
Well, the whole thing with like the mitigating with the EPRs and stuff, like I see that is even like a high ambient strategy in itself that gets overlooked is like defrost tuning, like making sure like the defrost is optimized and like the actual load of the store. Like I see more racks have issues or more units have issues when the defrost schedule's all crazy. You got some bigger loads during the day, or you're using electric defrost on the frozen doors during the day or the hottest part of the day. I see that causing more high ambient issues than a lot of other things. I mean, that I see is like one of the most overlooked by the customers in the US is defrost scheduling and the rack saturation being set too low, and you have cases just hunting all over the place. I mean, that's my biggest struggle right now is trying to convince people to tune that part of the system before they they're throwing gas coolers on with adiabatic when we really don't need it that much, or like they're trying other things when really it's a load issue.
Even if you would put the EPRs on there, right, for the same situation that we're talking about, where your lowest saturated suction and the coils aren't optimized as far as design, right? Because that's what he was talking about, basically design, changing the design of that. So if you were to put EPRs on there, it would actually give you a more of a constant load, right? Because instead of your electronic expansion valve being down to 5 or 10 or whatever small percent, or even closed because it's now maintained temperature, if you were to actually raise that saturated suction with via EPR, your electronic expansion valve would essentially load up more, giving you more mass flow, which means you've got happier compressors because they're running cooler longer, right? Does that theory make sense, or I'm just talking to my ass at this point? Because it made sense to me.
No, it makes sense. It's stability drives efficiency. So that's basically what you're saying is having a stable system at the end of the day is more valuable than anything else.
A super efficient system, because if it's not optimized, then it's going to still run like shit, and then you're going to lose that efficiency in the long, right?
Yeah. Control and stability. It's all comes down to that, and that again comes down to the more simple the system is, the better you can control it. I mean, I've seen systems hunt like no tomorrow, like crazy, just because of a simple set point of bringing adiabatic in. Like, let's again on the high ambient strategies, just bringing adiabatic gas coolers in. That set point was just too high, and they measured, or they didn't run it off of an ambient in a constant condition. They ran it off of the gas cooler outlet. What happened every time you bring water on, that the gas cooler outlet drops below the set point, they switch water off, it goes like that system. The whole day is just up and down all over the show, and the CO2 system does not like to be screwed around. When it runs, and that's why you say you always can laugh. Like, I always say, like, you never see a CO2 system run more stable than it does when it's running flat out balls to the wall transcritical mode. Then it's the most happy that it is. Like, it's stable as it's very, very stable. I mean, it's funny. We had one project, and I had the guy, I actually will see. I will look for that. I still have the video on my phone somewhere, and he phoned me up. He's like, you need to see this. He got the call. It was the service manager. He's like, he got the call out, saying that I think one of the cabinets like gave a bit of a alarm. It gave a high temperature alarm.
Mm-hmm.
So he went out, CO2 system, transcritical, parallel compression, and he looked at it and he was like, something doesn't make sense. And he looked at the graphs and he's like, it's fairly warm outside, but it's not crazy warm. And but the system is running absolutely flat out. Like, it's running super hard, it's running super flat. So he went check outside. So the end user, or the store owner, thought it would look pretty to put a roof over the gas cooler. So he basically thought it would look very pretty if you put a roof over the gas cooler. And that you obviously understand what happened there. But I mean, it took a video of the gauge on the discharge line for me. It was sitting on 1,800 pounds, but constant. But like, I mean, beautiful. Like, that system was running like a dream. And I mean, that's why I'm saying, like, that system was running smooth. Everything was like no valve hunted, no flash gas valve, no bypass valve, and that needle was just sitting on. It was like vibrating like its ass off, but on 1,800 psi, just sitting there. It's just controlling on its upper limit where it can run. But yeah, I mean, it was very funny, but I mean, it was very interesting to see. Like, it ran.
How far was the roof off the top, man? Like,
no, not very far. It looked pretty. Yeah, you couldn't see the gas cooler, but
we don't like the way it looks. All that metally stuff. We're gonna put some shingles on it. Look at chicken coop.
I'm sure fan motors love that. They were probably just screaming.
Yeah. But yeah, I must look for it. I think I have that video somewhere on my phone still. I must send it to you. You can see it's in bar, but you can convert it.
1,800 pounds. Holy shit.
Yeah, it was just sitting right there, but didn't move. Just
this is right a great podcast. Wynand, I want to do another one with you sometime and go over oil issues and dealing with oil during transcritical and subcritical, because we see a lot of issues running transcritical with oil. So a lot more oil movement, but that's a whole nother diatribe to go down.
I think if we get him talking too long, he's going to totally lose his voice. I can hear it. I can hear it start dwindling.
Sorry, man.
No. I feel bad that we have you. It's been an hour and a half now, and I feel bad. I'm like, oh shit. I'm sorry. Like, but
no issue. I know. I'm more than happy to come back again. Yeah, I mean, anything like doesn't matter. Yeah, let me know. I'll pop back on.
Awesome. Kev, you got anything else?
No, that's it.
All right, Wayne. Man, I appreciate you coming on. Just stay on the line, and guys, we'll talk to you later. See you next time.
Cheers, everyone.